Hi everyone, welcome back to Pythonic Pioneer. In this video, we will revise graph shortest path algorithms, mainly Dijkstra and Bellman-Ford, the two most commonly used algorithms for finding shortest paths between nodes or vertices in a graph. Dijkstra for graphs containing no, let's say, cycles, and also negative edge weights, and Bellman-Ford for detecting um, cycles as well as negative edge weights in a graph. So let's get started. What is the Dijkstra's algorithm? The Dijkstra's algorithm is like finding the shortest path on a map where you want to reach a destination with the least travel time. Imagine cities connected by roads where each road has a specific distance. This algorithm helps you find the shortest route from your starting city to any other city, which corresponds to the nodes in a graph. So you start at your current city, the source node, and consider all the nearby cities you can reach directly. You keep track of the shortest distance from your starting city to each of these nearby cities. Move to the nearby city with the shortest distance, and then keep going until you've finished all cities or reached your destination. This algorithm guarantees you find the shortest path because it keeps track of the shortest distances as it explores. It's like a traveler with a map always choosing the quickest route to reach the destination. Dijkstra's algorithm operates under the assumption that all edge weights are non-negative. It relies on the fact that once a vertex is marked as visited, its distance from the source vertex is considered final. Since it always chooses the vertex with the smallest tentative distance, there is no need to revisit vertices and cycles are not expected in the graph. Implement Dijkstra's algorithm to find the shortest path. So when you were given this is the code. We'll be using heap queue, which is our priority queue in Python. So you have this weighted graph represented in the form of an adjacency list, and for each vertex you have neighbor nodes and the corresponding distances. So this is the format that your um, graph is expected in, and this is what you'll be passing it along with the source node. So if you want to see the distance of this node to all of your other vertices, this is what you start with. This is your starting node. So initially a dictionary to store distances with all vertices is set to infinity. So this is set to infinity because we'll be having a min function, so like we're doing a infinity on that. So for each distance, each vertex, the distance is initialized as infinity. We set the distance of the starting vertex to 0 because it's like its distance from itself to itself should be 0. Now we'll create a priority queue to store vertices with their distances. Initialize it with the starting vertex and a distance of 0. So priority queue will have this tuple with 0 as the start, which is our distance, the shortest distance basically, and then the node. While there are vertices in the priority queue, you pop the vertex with the smallest distance from the queue. So this is where the priority queue comes in. Whichever vertex has the smallest distance, that is the one that you'll be popping first. So you get the current distance as well as the current vertex. If the current distance is greater than the known distance to this vertex, that means that something is wrong, maybe a negative edge weight or something, and then you need to continue. Else you just need to explore all the neighbors of this current vertex. So for each neighbor and wait in all the neighbors of this current vertex dot items. It's important, the syntax. Calculate the new distance to the neighbor through the current vertex. So distance, the new distance will be the current distance plus weight. If this new distance is shorter than the known distance to the neighbor, so let's say the neighbor has been initialized to infinity or some number, and from this node the distance is shorter, then update the distance to the neighbor. So update the distances of neighbor, this array. Is it an array? No, it's a dictionary, right? So update this neighbor's distance to this new distance and add the neighbor to the priority queue with the new distance because this was recently updated. So add the neighbor to the priority queue with the new distance. So this will keep adding in till all the nodes are exhausted, because most of them initially is infinity, and whenever you go to a new node and find a new path, that will definitely be less than infinity, so you'll be pushing like the neighbors to the priority queue with the new distance. So quick recap: initialize the dictionary of distances to infinity for all vertices, initialize the distance of the starting node to 0, create an empty priority queue with the 0 distance and the start node, pop from the priority queue while the priority queue exists, and if the current distance is less than some previous distance, then continue. Right. And now explore the neighbors of this node, get the neighbors name of the node and the weight. Now if you have to calculate the distance, you'll be calculating it with the current distance of the starting node plus the weight, and if this distance is less than the existing distance, then update the distance to the neighbor and add that to the priority queue. That's it, return the distances. So that was it about Dijkstra's algorithm. If you attempt to use Dijkstra's algorithm on a graph with negative edge weights, it may not work correctly. It can produce incorrect results. Additionally, if you apply it to a graph with cycles, it may not terminate the loop because it can get stuck in an infinite loop. For graphs with negative edge weights or cycles, other algorithms like Bellman-Ford algorithm are more appropriate, as they can handle such scenarios by detecting negative edge weight cycles and ensure termination of the loop. Right, so coming to Bellman-Ford, implement the Bellman-Ford algorithm for finding the shortest path, including handling negative weights, is what the main focus of this is. The Bellman-Ford algorithm is like finding the shortest path in a network of roads where the roads can have positive or negative lengths, and there might be shortcuts or loops. The goal is to find the shortest route from your starting point to any other point in the network. So here's how it works. Start with your current location, the source. Consider all roads that lead to nearby places one at a time. For each road, check if taking in it would make the path through the nearby place shorter than what you've found so far. If it does, update the shortest path. Keep repeating for all roads until no more improvements can be made. This algorithm guarantees that you find the shortest path even in complete networks, because it keeps trying to improve paths until there are no more changes. It's like exploring all possible routes systematically to find the best one, considering positive and negative lengths and loops. So this is the Python code for the Bellman-Ford algorithm. Initially we have a weighted graph just like we had in Dijkstra in an adjacency list format with the weights. It's like a dictionary of a dictionary. It could also have been a list of tuples, but yeah, even this is good. This works. So there's this Bellman-Ford function which gets in the weighted graph and the starting node A. So this function takes in the distances. This doesn't take in the distances, it takes in the graph and the start vertex. First, we initialize the distances like we did in Dijkstra with an infinity. Initialize the distance of the start to 0, again like how we did in Dijkstra. Relax all edges repeatedly. So for, let's say, we'll basically be doing this for all the nodes in the graph, so n times. So for each vertex edge in graph.items, if like for neighbor or weight in edge.items, if distances of vertex plus weight is less than distances of neighbor, that is the neighbor distance. So this new distance that we are calculating, distance of vertex plus weight, if it's less than the existing distances, then update that distance of that neighbor and check for like, so this happens like the total number of vertex number of times. And if you want to check for negative edge weight cycles, just do it one more time and see if the distance is reduced further. If it does, then you can raise an error that there is a negative weight cycle. So this is how it detects the negative weight cycle. This code finds the shortest paths from a specific starting vertex to all other vertices in a weighted graph using the Bellman-Ford algorithm. It starts by initializing distances as infinity for all vertices except the starting vertex, then iteratively relaxes the edges to update the distances until no further improvements can be made. It also checks for negative weight cycles in the graph. So it relaxes these edges how many times? The number of vertex times. And if when you do it for another time, if the edges get more relaxed, the distance is reduced, that means there's a negative edge weight cycle. So mostly it's this kind of similar, just that the main points differ. In Dijkstra, we have a priority queue, which is different, and we keep popping the least like we keep popping the vertex with the smallest distance from the priority queue and keep updating the neighbors and relaxing the edges till there is something in the priority queue. If we find a new distance which is less than the existing distance, we update the distance of the neighbor and push that neighbor into the priority queue with a new distance. And this is very important. If the current distance is greater than the known distance to this vertex, then skip it. This is also very important. This is the main part, and in Bellman-Ford, we um, relax the vertices, that is, go through all the neighbors and weights in the edges. What's edges? Okay, right. Right, so for all of these edges, right, so for each of these edges, you go through like that vertex. So for one vertex, you'll go through these for edges, and then for this, and then for this, and then for this. So when you're going through these edges, each of these edges, you just relax them, and the updated distances are calculated. Only if that distance of that existing vertex plus the new weight is less than the pre-existing distances of neighbor. But if you do it once more after, you know, going through all of the edges, that means that there is a negative weight cycle. So you need to raise a value error. That's it. Thanks for watching. Hope this was helpful. Have a great day.